Shall we begin? The answer is coming. I can do this all day.
Tear down this wall.
Ikuzo means let's go, and here we come with the greatest story ever told, the story of the stardust, where we explore the vast expanse of space and the mysteries that lie within it. Powered by Jägermeister and joined by an acclaimed astronomer and professor at the University of Arizona with over 40 years of experience in the field and extensive research on topics ranging from the formation of the galaxies to the search for extraterrestrial life. He has also authored several books, including The Living Cosmos and How It Began, A Time Traveler's Guide to the Universe. In this episode, we'll delve into some of the most fascinating and mind-boggling questions about our universe, such as the possibility of life beyond Earth, the origins of the universe itself, and the mysteries of dark matter and dark energy in an awe-inspiring conversation with Professor Chris Impey. Professor Impey, are you ready to go genuine, uncensored, and unscripted with us today?
Yes, glad to be with you. I'm ready.
Well, before we go on our Cosmos Odyssey, Professor Impey, can you tell me how you became an astronomer? Was a gaze in the night sky when you were a kid enough, or is it something that you figured out later in your life?
Yeah, astronomers happen two ways. One is they get hooked on a night sky when they're young and kids. I grew up in cities, New York, London, so I never had stars and I never had a dark sky. The other way is through physics. So I was a physics student as an undergraduate, and physics is sort of the gateway drug to astronomy, because when you study physics, you can look at the physics of very small things and subatomic particles, or you can take the physics out and say, wow, we can use physics to figure out how the universe works. So that's how I got into it.
So we are beginning to explore the universe beyond our galaxy. And what are the biggest challenges in observing and studying distant galaxies? And what do you think we can learn from them?
I mean, the challenge is the distances and the brightness. The things are so faint. So we're talking about things that are billions of light years away. These galaxies that were studied with the Hubble Space Telescope or James Webb, they are 10, maybe 100 billion times fainter than you can see with your eye. So you need enormous telescopes on the ground or in space to study them. And that's one of the big challenges.
Yeah, let me quote you from your book, The Living Cosmos, a fabric that binds art and science. In a universe ripe for biology, it is natural to speculate on the existence and nature of biology elsewhere. Can you further elaborate, as the astronomer, this relatively new and unexplored term, astrobiology, at least to our broader audience and to us?
Sure. Astrobiology is a very exciting field in astronomy. It's a subfield. This is the search for life in the universe. It also involves understanding how life evolved on the Earth, because still we only know one place with biology, this planet. So we have to learn as much as we can about what happened here to understand what might happen elsewhere. So I got interested in this some years ago. I just wrote a book, just came out, called Worlds Without End, which is about exoplanets. And so after speculating for centuries, astronomers started to find planets orbiting other stars. The first was found in 1995, and we have over 5,000 now. So we find them quite easily. And the next step in this research is to try and figure out if any of them are actually hosting biology. We found a number that are Earth-like, or they're similar to the Earth in many ways, but we don't know yet if any of them have biology on them.
Oh, yeah. But tell me this, because we tend to obviously research it from a standpoint that we know. Now we know that in order to have life, you need water. But do you think that maybe, and obviously we research it because we know that life exists here because of water and magnetic fields and etc. But do you think, is there a possibility maybe that life can originate from something else? I know it's a little bit speculative, but do you think it's a genuine possibility that, we cannot explore because we don't have the mind yet for it?
That's right. That's a big problem in this field, because we have only one example of biology and we learn a lot from how life evolved on the Earth, but it may not be the only way biology works. So biology on other planets might be quite different, quite strange. It might not need water. It probably will need carbon. We don't know, but it probably needs some ingredient to make complex information bearing molecules. But it could be very different, and especially the nature of the life forms and the creatures that evolve after billions of years, they could be completely different, alien from anything we're familiar with. So it's a challenge to think about these possibilities because we only know this one thing. We know it very well, and we know that it doesn't have to be the same elsewhere. So science fiction writers, of course, have speculated about this for a century, and scientists are speculating too, and they're trying to do it in a careful way so they stay inside the boundary of science. But the truth is we don't know. It could be very strange life elsewhere.
Yeah, when we had Dr. Matt Rowe for an interview, he said something similar and really thought-provoking when I asked him why we always search for water and carbon-based life forms. And I'll paraphrase, but he said, among other things, that what if our concept of water is not the only form of the liquid water out there? How would that affect the search for extraterrestrial life, actually?
Well, I think biologists and chemists are quite clear that if life needs a liquid medium, perhaps, to exist in, it does not have to be water. So to take an example, we have Titan, the large moon of Saturn, and it has lakes and it has hydrocarbons, but it's a very cold world, and there's very little water there. Those lakes are extremely cold, and it's ethane, methane, a little bit of ammonia, and a little water. And people are speculating maybe there's a strange form of life in those lakes where there's almost no water at all. So you definitely don't have to have water. Carbon is a little different because carbon is unrivaled as a molecule for making complex, stable, and infinitely complex molecules. Carbon chemistry is infinitely complex. And silicon may be in the same line in the periodic table, but chemists who study this say, well, yes, you could have complex molecules based on silicon, but they're not as stable and they're not as diverse as carbon. So carbon is the best. So we imagine that carbon is the information storing molecule or atom that's based on a molecule is the best one. But maybe you don't need cells. Maybe the container for life is not based on a cell in other places. So the whole architecture of life might be different.
Yeah, but that would, if we somehow discover that, our whole perception of life basically and our species would change. That would be something totally crazy.
It is, and the scientists have a problem with this because, you have to design an experiment. So you design the experiments to look for what you know, and then at least you get an answer. You can say, no, it's not carbon-based chemistry. No, there's no DNA or no replicating molecule like we have, or nucleic acids. But if you don't know, if you're looking for strange forms of life, how do you design an experiment? How do you know whether you found something or not found something? So the science of looking for strange life is tricky because you tend to look for what you know, not because you have no imagination, but just because then you can get a result. You can get an answer.
And every now and then we get these stunning images from the James Webb Space Telescope, like most lately one of the Uranus. But the James Webb Space Telescope is meant to answer many other questions and probably ponder many new questions as well. And one of James Webb aims is toward the exoplanets and habitable zone, which we are speaking about, and they are part of your research. What's more likely with those planets, to find our new home in a distant future, or our first neighbors?
James Webb will do some of this research, but people forget that James Webb was designed before exoplanets were ever discovered. So it's not really optimized for this experiment. It's going to do the experiment as well as it can, but it's not the best tool, actually. There are 3 huge ground-based telescopes that are all under construction. My university is part of one of them. And these are much bigger than the James Webb, and they will take very sharp images. And they are going to do this experiment actually better than James Webb, which is to look for Earth-like planets and to try and sniff their atmosphere of those Earth-like planets for molecules that are associated with biology, like oxygen or ozone or methane, and to look for water vapor, of course. So that's going to happen. Those experiments will happen within a few years, I think.
And given with the sheer number of exoplanets discovered so far and the likelihood of many to come, what does it mean for our understanding of our place in the universe if we find the other Earth-like planets with maybe even intelligent life not so rare as previously thought?
It means that we're not special. So everything in the history of astronomy says there's nothing special about our star, our location in the galaxy compared to other galaxies. There's nothing special.
How dare you?
About our place in the universe. And so maybe biology is special to this planet, but that would be against the history of the subject if that were the case, because the ingredients for biology are everywhere, are widespread. So astronomers anticipate there is life elsewhere, but it's a very difficult experiment, and it will not probably be a nearby object. The nearest Earth-like exoplanet may be 100 light years away. That's really like the Earth, and that's very far. That's thousands of trillions of miles. So these are not neighborhood objects; they're very distant.
Yeah, you're right. In one of your books, you wrote the quote: "The final step in Copernican revolution would be to find out that we live in a biological universe, and to find out that yes, we are not special."
Right. And then the question is, what kind of not special are we? Is the biological universe just filled with microbes and very few complicated creatures? Remember, on Earth, it took 3 billion years. There was life on Earth for 3 billion years before anything big enough to see without a microscope. So most life on Earth is microbial for most of the history of the Earth. And it's still true. Most of the genetic diversity of life on Earth is in the microbes species. And maybe that's true in the universe. Maybe complex life, plants, animals, creatures like us, maybe that's actually quite rare. We don't know, but we're looking for them too, with different methods than the ones we're looking for microbes.
Yeah. And we made an effort to get an answer on how everything started, especially now with images from James Webb, like we mentioned. And now, and that's how we got the Big Bang. But that is just a part of the jigsaw of the cosmos origins. Will we find the answer to what was the nothing before the Big Bang? Nothing that created everything. Do you think we will ever go beyond the Big Bang?
Well, people are trying. So the theorists are speculating. The Big Bang is a very sturdy, robust model. It has observational evidence. It's been around for 70 years and has passed a lot of tests. So it doesn't answer the question of where did it come from and what came before. So that the Big Bang model does what it does, which is describe a history from a very dense, very hot state, but it doesn't answer some questions. And so people speculate about what came before, what caused the Big Bang. And this is sort of, unfortunately, beyond the realm of confirmed physics. So people will have to go to something like string theory, or they'll have to go to some multiverse, some theory of the multiple universes, because they all spawn from quantum events. And immediately you do that, it's very exciting, it sounds very interesting, but you're also out of the realm of conventional physics. And so it is pretty much speculation to ask those questions and try and answer them so far. Maybe there will be a way to have evidence about what happened before the Big Bang or the existence of parallel universes. Maybe someday there'll be evidence for these, but not right now.
Yeah, but when you're looking, for example, at exoplanets, and of course we were talking about some that look a lot like Earth, even the similar solar systems. Do you think that maybe by, this is hypothetical, but by the end of this century, we could, genuinely travel through our solar system to some distances?
I think the space travel part is hard because physics is a limit on this. We will be able to send very small probes, nanobots, miniaturized probes with sensors. We'll be able to send those beyond the solar system soon. We have technology to do that. We maybe attach a solar sail to them and we can send them to another star system. They'll take a while to get there because we can't get them to a very large fraction of the speed of light. But getting humans and getting large objects, spaceships, out of the solar system is extremely hard. The energy cost is enormous to go any speed. And so the missing ingredient we would have to travel beyond the solar system is suspended animation for humans. We'd have to have some way to put humans on ice or make their metabolism extremely low so they could
Like
yeah, they would have to survive a multi-century journey to get to a nearby star system. It's not impossible. It's technology. Those are medical technologies, essentially, that are people experiment with, but we don't have mature yet. But if we did get them mature, then at some point, yes, we could leave the solar system.
Yeah, and I saw that currently there are some researchers in this field that actually on one university that they succeeded in making rat stay in this cryptostasis for 4 days and revive them again after that. But
Yes, and other research has used, so these are animal models for us, and the other animals that have been used in these experiments are dogs and pigs, and similar results. They've taken these animals down to 1% metabolism or something like that for weeks, up to weeks actually. And the rate of reviving them successfully is not perfect, of course. It's only 10, 20%. So I'm afraid they're dead animals as a result of these experiments. But they're just the beginning of trying to do it for humans. There are huge ethical issues, of course, as soon as you do it on humans.
oh yeah, and we spoke about unconventional physics, and another field of unconventional physics is maybe black holes, right? So what happens to the information that falls into a black hole? Can projects like Event Horizon Telescope help to solve this information paradox?
I don't think they can. The Event Horizon Telescope has made several spectacular images of black holes and their immediate surroundings, but it's not addressing the properties of the event horizon or being able to ask those deeper questions. So there is still theoretical debate. There's a lot of theoretical debate. Probably, I don't know, a couple of hundred research papers a year are written on black hole theory, the event horizon, the paradox of information, and so on, without really an obvious resolution. The problem is that our gravity theory is incomplete. And so Stephen Hawking put it nicely. He said the black holes contain the seeds of their own demise, which means that the prediction of a singularity at the center of a black hole is a place where your gravity theory blows up. It means it doesn't work anymore. So the theory is not completely consistent as far, it predicts black holes. General relativity predicts the existence of black holes, but it doesn't fully explain them. So we actually are lacking some theoretical ideas that we would probably need to understand the information paradox and things like that.
There are no rules but one. Drink Jägermeister at minus 18 degrees Celsius.
Yeah, that's problematic. Tell me this. I wanted to ask you. Our magnetic field is very important to us. Very important. But when I read on the exoplanets, and I don't know, maybe I read some older research, I don't know. One of the keys to the research is finding if we could exoplanets that have something similar to the magnetic fields. Has something like that been discovered? Have discoveries been made? Observations? What is the status on that?
So you're right. Magnetic field is very important for life on Earth, of course. It protects us from cosmic rays and solar wind. Mars, for example, has weak or absent magnetic field, and it's uninhabitable on the surface.
We saw how that ended.
Also, this thin atmosphere too. So exoplanet data is not detecting magnetic fields directly. There's only indirect inference of magnetic fields on exoplanets. If you see an exoplanet that's massive enough that it almost certainly has a metallic core and it has plate tectonics, then it also probably has a magnetic field like the Earth. So you can predict magnetic fields on exoplanets from their global properties, but that's a statistical statement. It doesn't mean you actually measured the magnetic field. That's beyond the observation right now.
That's disappointing. And this story of the stardust sounds poetic. The fact that every atom in our body was once a part of a star billions of years ago. But so if we are made of the stardust, does that mean our lives are written in the stars, or were we just a cosmic accident waiting to happen? I mean, do you think, what is life just happened by chance, or is it something that that needs to happen regularly? That nature almost intends happen.
Right. So it's always dangerous to look at your own history and to draw a conclusion like, I'm here because I had to be here, or life on Earth is here because it was inevitable or had to happen. And that's why the experiment of finding life elsewhere, even if it's just microbes, is so important. Because as soon as we find microbial life elsewhere, even if it's only a few examples, but if it's abundant, then we know that it wasn't a fluke, that it wasn't an accident, that the universe is not only made for life, but tends towards life as time goes by. So we know the universe is getting more hospitable, back to the stardust idea. The universe is more hospitable for life as it gets older. And we came into a universe, we are born in a universe that's 14 billion years old almost, and we shouldn't necessarily be surprised because very early on there wasn't any carbon, and for quite a while there wasn't probably enough carbon or heavy elements to make biological creatures. So the universe is getting more hospitable for life as it gets more life's ingredients spread throughout to become part of planets and stars and people and so on. But that still doesn't mean it's inevitable. Until we find that second example, that third example, we won't know. And if we fail, I mean, if in 10 years we've inspected a dozen or 24 exoplanets that are Earth-like and have all the ingredients for life, and we are fairly sure there's no microbial life on them, then maybe it is a fluke. Maybe we are a fluke.
How you gonna figure that out if there is microbial life there? What method is used?
Yeah, so it's taking the research to another step, another level. The first exoplanet was found in 1995, and now we have 5,300. So finding exoplanets, not too hard. I mean, find them all the time. We have a lot. But detecting life on an exoplanet means a very difficult experiment. We have to isolate the planet from the much brighter star, 100 million, maybe 1 billion times brighter starlight, suppress that starlight, and then take the feeble reflected light of the planet, smear it into a spectrum, and look for biomarkers or signatures of microbes. Oxygen, ozone, methane, things like that on the Earth are indicators of life, and there are others. So those are just hard experiments, but we're almost able to do them. James Webb has done the precursor experiments, but not on Earth-like planets yet. And these huge ground-based telescopes under construction will be able to do the experiment on Earth-like planets in a few years. And that's the experiment we're on the edge of being able to do, which is very exciting because it's, finding a few more exoplanets when you already have 5,000 is not so exciting. But measuring the microbes, the trouble is that it's not a definitive experiment. It's a difficult experiment. The data will be noisy, will not be as satisfying as you want. And also it's very hard to, it may not be decisive because you can get, for example, geologists will tell you can get oxygen in a planet atmosphere that has no biology. You can have very interesting geological processes. Oxygen is very reactive. It doesn't stay in an atmosphere, but you can replenish it with geology. So oxygen is not necessarily indicating life. So, and then the converse of proving that life doesn't exist on a planet, that's hard too. And also for reasons we talked about, that if the life is a little different, you're looking for the wrong thing. And so you can't rule it out. So proving that we're unique is probably not going to happen actually, just because we don't know how strange biology could be in other places.
Yeah, and even if we get to know that life is present on some of the exoplanets, how do we figure out how long life has been present on that planet?
That would be beyond these kind of experiments. These experiments, we just have so little information about these exoplanets. They're far away, they're incredibly faint. So at the moment, we just measure the mass or the size. That's all, nothing more. For some subset, we will eventually measure the atmospheres, what's in the atmospheres of those planets. And we hope that sometimes it will indicate biology. But we don't know anything beyond that. We don't know the history. Well, we can say how old the planet is based on how old the star is that it orbits. But we can't tell about the state of evolution. There's also a set of experiments with these atmospheric tracers, which they're looking for technosignatures. So biosignature is just a chemical marker for life, biology, like oxygen, ozone. A technosignature is interesting because it's a gas that is produced only by technology, not just by microbes. So nitrous oxide is an industrial pollutant. We could look for that in the atmosphere. Chlorofluorocarbons are things that, refrigeration has put into ozone layer and almost destroyed it. And now we apparently have some more. So we can have atmospheric gases that are only, to our knowledge, produced by technology. And then we'd have an indication of advanced creatures with civilization and technology. That would be exciting. And the same data you can look for both.
Yeah. No, I mean, is it possible that genuinely we just came first in this universe?
It would be possible. Again, it's possible we're unique and first, but the universe is very old. And so because of the rate of carbon and heavy element production, there was a very early phase of galaxy formation and star formation. So the universe was a very busy place making stars and heavy elements early on. And so you can pretty much say that within 1 billion years of the Big Bang, you could have an Earth clone. Just imagine a planet that's as close to the Earth as you could imagine. You could have that 1 billion years after the Big Bang. Well, that means you could have an Earth-like planet that had a 7 billion year head start on us. And
yeah, that's interesting.
So that's why it's not a rigorous argument, of course, because you don't know, but statistically, it seems unlikely we would be the first biological creatures or the first living planet. And all the ingredients have been in place for billions of years before the Earth even formed.
And you mentioned there the first galaxies, and James Webb is picking up some new data that actually disapproves our current beliefs on the forming of the galaxies. So what about it?
It's interesting. It's very interesting data. James Webb was designed, it will do exoplanet work, of course, although it wasn't built for that. And it was designed, however, to find the first light in the universe, the earliest stars and galaxies, within a few 100 million years of the Big Bang. And the galaxies it's finding that are almost that far back are much bigger and brighter than anyone expected. And that's interesting. It's exciting. It's sometimes being stated as a problem for cosmology or the Big Bang, and that's not true. It's not. The data does not say that. The data does not bring the whole cosmology and put it in doubt. What it does, though, is tell us that we don't understand how galaxies form and grow early in the universe very well. We have models, we have theories, we make simulations in computers, and the galaxies that James Webb is finding are not completely bizarre or impossible to predict or produce in a simulation, but they're challenging for the simulations to predict. So there's a tension there. There's a little tension with the cosmology model we have and the discovery of these galaxies, but it's not at the level of we got to toss it out and find some other cosmology.
Isn't it fascinating how small we are?
Yeah, the thing that's challenging about these galaxies is that they grew so fast. They probably had black holes that grew very fast in their centers. But remember, the universe in this era that James Webb is looking at, these are redshifts of 10 or 12. That means the universe was 10 times smaller and 1,000 times denser than it is now, and 10 times hotter. It was a very different universe that it's looking at. And when the universe is 1,000 times denser, it is easier for things to collapse, easier for things to form. Everything goes much faster. So there was a very rapid phase of construction of galaxies and black holes that the centers of them in this early universe. And we're just learning about it. And we don't fully understand it, but that's why it's research. That's why it's exciting.
And what about dark matter and dark energy? What if those two are actually two manifestations of the same underlying physical phenomenon rather than two separate entities as currently believed? Could that be possible?
So astronomers...
That the dark energy...
Yeah, astronomers
go on.
Sure about both, of course. There's more certainty or understanding of dark matter than dark energy. There's no obvious indication they're related. They actually seem different. Dark matter is a material substance, probably a fundamental particle that pervades space and feels the force of gravity, but not the electromagnetic force. Dark energy seems to be a property of space-time itself, causing the expanding universe to accelerate in its expansion. So they seem qualitatively different. They're not obviously related. Astronomers understand dark matter better because we've been measuring its effects for half a century or more in the way galaxies rotate. That was how it was first inferred. And now we have gravitational lensing and other tools to measure dark matter and map it out. So we know a lot about dark matter and where it's distributed and how it's distributed on the scale of galaxies or larger than galaxies. But we just don't know what it is. We don't know what the physical entity is. Well, we've ruled out a lot of things. We know things that it's not. It's not black holes. It's not substellar objects. It's not rocks in space or dust particles in space. And we've almost ruled out all the big stuff down to the level of a subatomic fundamental particle. And that's where people think the answer is. Unfortunately, physics is not helping here because the Large Hadron Collider is not finding the most plausible candidate for a dark matter particle, nor are underground mine experiments that are looking for it. And so this is potentially heading towards a crisis for physics and cosmology if we don't identify the dark matter particle in the next 3 to 5 years. Then there's problems. Problem for physics because it's anticipated that it will emerge from the symmetry theory, a supersymmetry theory. And then if you have to throw those theories out the window, that's a problem for physics. Problem for cosmology because it means you may have to accept the fact that maybe the gravity theory is wrong. Rather than there being dark matter that you have to find and understand, maybe Newtonian gravity is not correct on large scales. It's possible. So this is an interesting time for dark matter, but we should approach some understanding or resolution. Dark energy is so different. There's so little information about it. It's hard to measure. It's hard to characterize. We have no physical theory for it. All the physical theories we've tried, they don't really work. Physicists love to speculate, but they don't really have any good suggestions for dark energy. So it's sort of in a different category than dark matter at the moment.
I hope you liked our questions. They are powered by Carl Sagan and Martin Freeman, basically. But I hope you enjoyed this talk.
And I like we covered a lot of ground, talk about everything from planets to cosmology. I enjoy free-ranging conversation.
Yeah, but before we wrap up, we have a little tradition where we say a quote or verse on our Montenegrin language and translate it to English. And I pick a quote from our poet Jevran Brković. And he said, riječ koju danas kažeš mora biti ti. Prošla su vremena kada si ih prosipao, kada si ih imao kao pljeve. And translated to English, it would be, the word you say today, it has to be you. Times has passed when you spilled them, when you had them like chaff. And I hope you liked it.
Yes, that was fun.
Yeah. Unfortunately not connected to cosmos or astronomy, but okay. Thank you for this opportunity, Professor Impey. Thank you.
Yes, I enjoyed our conversation. Thank you.
We stay genuine, uncensored and unscripted, and we always will, as we have to order our usual. Share us and subscribe us, and stay tuned until the next Wednesday. Iguzo!